Now listen here. If a stream of a gas at a high pressure is allowed to expand by passing through a porous plug into vacuum or a region of low pressure under adiabatic conditions, it gets cooled appreciably. This is called the Joule Thomson effect. And normally for all the gases, a cooling effect is observed except for hydrogen and helium. Hydrogen, it shows a cooling effect only below minus 80 degrees centigrade, and the helium shows a cooling effect below minus 240 degrees centigrade. So the phenomenon of a change of temperature produced when a gas is made expand adiabatically from a region of high pressure to a region of extremely low pressure is known as a Joule Thomson effect. Now, why this cooling is taking place? The cooling is due to the decrease in the kinetic energy of the gas molecules. See, when the gas molecules are compressed, when we are enforcing these molecules to be together, they develop some kind of van der Waals force of attraction among the gas molecules. So the gas molecules are close to each other. Now, when we are allowing these gas molecules to expand suddenly, what happens? They break this van der Waals force of attraction and they go far apart. And because of that, the part of the kinetic energy is used for overcoming the van der Waals force of attraction. So that energy is taken up from the surrounding. That is why the kinetic energy decreases and also the gas experiences a cooling effect. Now look here. I don't want the students to disturb the class. If you want to enter on time. So look here, it is expanding to vacuum. So the delta U is equal to 0. So at a constant temperature, you all know that dou U by dou V is equal to 0. Actually, this particular quantity dou U by dou V is called the internal pressure. So the internal pressure of an ideal gas is always shear 0 because ideal gases are not having intermolecular interactions. They neither attract each other nor repel each other. So the internal pressure of an ideal gas is 0. Now look here, this is a system to explain the Joule Thomson effect. What is at the center is the porous plug. So this is the porous substance, and on the left we have a piston. This is a piston A, and on the right we have a piston B, and you see the pressure on the side A is P1 and there is a volume change V1. So I am compressing this pressure. I am just moving this piston towards right so that this was the old position and this is the new position. So there is a change of volume V1. And this gas is slowly, it goes through the porous plug and goes to the right side piston, and here the pressure is P2 and here the volume change is V2, where this was the position of the piston and it is expanded to here. Now the work done on the system at the position A, look here, on the system A, the surrounding is doing the work on the system, so it is plus P1 V1, or P1 is the pressure, V1 is the volume change. Now work done by the system, this side the system is doing the work on the surrounding by the piston B is minus P2 V2. So what is the net work done? So on one side the work is done by the surrounding on the system, on the other side the work is done by the system on the surrounding. So net work done is minus P2 V2 plus P1 V1. So the minus P2 V2 plus P1 V1 is equal to U2 minus U1. That is the internal energy change. So internal energy change is the net work done. So net work done, what we calculate, because the internal energy is not a directly measurable quantity. So what is the internal energy change and what actually has happened is the minus P2 V2 plus P1 V1, which is equal to U2 minus U1. So when I bring this U2 This side, it becomes minus U2, and then this P1 V1 goes to minus P1 V1. When I adjust the signs, what I'm getting is U2 plus P2 V2 is equal to U1 plus P1 V1. So this entire quantity is called H2, and this entire quantity is called H1. So this indicates that the enthalpy at the side B is same as the enthalpy at the side A, which means that during this process, there is no change in the enthalpy. So delta H is equal to 0, which is called isenthalpic process. So in the last class itself, I have explained what is isenthalpic process. There is no change in the enthalpy during the process. Now, you know that dH is a complete differential. It is also a state function. When we first started studying the enthalpy, there itself we discussed that it is another state function. What is a state function? Which depends only upon the initial and the final states of the system, and it is not depending upon the path by which the system has arrived at the new state. So the new state function is dH. dH is another complete differential. So the dH can be presented like this. dH is equal to dou H by dou P. That is, it changes with pressure when temperature is maintained a constant multiplied by dP plus it's a change with respect to temperature when pressure is maintained a constant into dt. Now you know that this particular value, that is dou H by dou T at a constant pressure, is nothing but the heat capacity of the gas at a constant pressure Cp. So I can rewrite this equation like this: dH is equal to dou H by dou P at a constant temperature into dP plus a Cp dt. You know one thing, the dH is equal to 0 because the entire process is isenthalpic process. So for an isenthalpic process, the enthalpy change is 0. So I can write dou H by dou P at a constant temperature into dP plus a Cp dt is equal to 0. So from this I can relate that dt by dP, that is the change of temperature with the pressure, is equal to minus dou H by dou P at a constant temperature divided by Cp. So this particular quantity is called Joule Thomson coefficient. So dou T by dou P at a constant H is equal to minus dou H by dou P at a constant temperature divided by the heat capacity of the gas at a constant pressure. So this is called the Joule Thomson coefficient. So using this Joule Thomson coefficient, you can very easily relate the temperature change with the pressure change. So which is conventionally written at the bottom, delta T is equal to minus dou H by dou P divided by Cp into delta P. So if you are aware of the delta P, you can very easily find out what is the delta T, the temperature change which is corresponding to the pressure change of the system. Now look here, I'm going to calculate the Joule Thomson coefficient of an ideal gas. Look here, this is the definition. Dou T by dou P is equal to mu Jt. What is mu Jt? That is called the Joule Thomson coefficient, which is equal to, just I have simply rewritten this equation. Actually, this equation will look like this. It is dou H by dou P at a constant temperature divided by Cp. I have taken the Cp out. It is minus 1 by Cp into dou H by dou P at a constant temperature. So the minus Cp can be taken out. So what you are getting is the H can be expanded and can be written as U plus PV, because enthalpy is internal change plus the work done. So dou H can be written as dou into U plus PV. So this you are getting minus 1 by Cp into dou U plus PV by dou P at a constant temperature. Now, in order to have a further simplification, I am writing this equation like this: minus 1 by Cp dou U by dou P, this is taken as a separate term, and dou PV by dou P, that has taken, we have taken that as a separated term, and both are taking place at a constant temperature conditions. Now what I'm doing, I want to change this into some other factor which I know. So I multiply and denominator and the numerator by one single unit, which is dou V. So what I'm doing, this can be written as dou U by dou V into dou V by dou P plus dou PV by dou P at a constant temperature. You know one thing, the entire term is a zero. For an ideal gas, dou U by dou V is equal to zero. So this entire term becomes zero. And this side from the graph, what we have already studied in the gaseous state, dou PV by dou P at a constant temperature is a zero. So everything is a zero. Therefore, this is zero. That is the mu Joule Thomson coefficient for an ideal gas is zero. So the ideal gas doesn't show either heating effect or cooling effect. It is because the Joule Thomson coefficient of an ideal gas is zero. Now we are going to find out Joule Thomson coefficient of a real gas. What is this real gas? The gas molecules which have intermolecular interaction. They are called the real gases. So the real gases expand and work is done in separating the molecules against the cohesion force. Actually, this work is stored as a potential energy in the gas molecules. So the potential energy of the gas molecule increases and at the same time no heat is gained because the entire system is taken in the adiabatic condition. So as the no heat is gained, a corresponding amount of the energy has to be converted into kinetic form because the total energy of the system is supposed to be constant if at all there is no heat energy is observed. So what happens is the potential energy of the gas molecule increases. If no heat is gained by the system, the kinetic energy is supposed to decrease by an equivalent amount. Hence, the temperature drops down. But for an isothermal process, there is a net increase in the energy because the isothermal, we are going to maintain the temperature constant. The quantity of the heat energy which is lost by the decrease in the kinetic energy is supplied from the surrounding, which maintains the temperature constant, and consequently the total energy of the system increases. So what happens in this situation, dou U by dou V becomes a positive and dou V by dou P becomes negative. So what happens when you want to calculate the Joule Thomson coefficient? It is minus 1 by Cp into dou U by dou V at a constant temperature, dou V by dou P at a constant temperature into dou PV by dou P at a constant temperature. So from the discussion that we had in the gaseous state, for a real gas, this particular unit is positive, this unit is negative, so they are in multiplication. So this entire unit becomes negative. There is already a negative here, and this side dou PV by dou P is also negative according to gaseous state. You can refer the gaseous state chapter in the book. So at ordinary temperatures, what happens? Look here, PV decreases with increase in pressure for real gases, except for helium and hydrogen. So dou PV by dou P becomes negative at ordinary temperatures. See, here is already a negative, and this is a positive quantity, and this is a negative quantity. So their multiplication, it gives a negative quantity, and this entire unit is negative. So let us see what happens. Look here, at ordinary temperatures, Cp is positive, this is positive, this is negative, so whole negative, this is already negative. So what happens? Mu Jt is a positive for real gases at ordinary temperatures and at low and moderate pressures. Thus, when delta P is negative, delta T also negative. Therefore, when pressure decreases, temperature drops down. When pressure becomes exceptionally high, what happens? At high pressures, dou PV by dou P at a constant temperature becomes a positive. So in earlier cases, it was negative. Now it is positive. So what happens? This entire unit almost remains constant, but with a negative sign. But this thing becomes positive and goes on increasing with the pressure. So what happens? When pressure increases, this particular term increases in positive scale. So up to a particular point, this entire term becomes zero. And after that, what happens? It becomes negative. So at this condition, the temperature will increase. So at this condition, mu Jt decreases with the pressure and becomes zero at a particular pressure, then becomes negative. So the value of the Joule Thomson coefficient changes with the pressure. So at moderate pressures and at ordinary temperatures, it's positive. And then when pressure increases at a particular point, it becomes zero. It becomes zero means it doesn't show any cooling or heating effect. After a particular pressure, it becomes negative, and which means that starts showing heating effect. So that is what is actually we have seen. Look here, look at this equation. Now you can understand, but you have to observe with the fullest concentration, then only you will understand. I am writing this real gas equation. Real gas equation I have already written in a different form. Now it is a different form so that we can mathematically approach the Joule Thomson coefficient. See, PV is equal to RT minus A by V plus BP, where A and B are real gas constants. Look here, this V can be written as RT by P. So PV is equal to RT minus, in the denominator it becomes RT by P. So that becomes the multiplication of inversion. So what happens? P goes up, RT comes down. So AP by RT plus BP. So now what happens? I divide everything by pressure. So V is equal to RT by P. This side, this P gets cancelled. This side, this P is also getting cancelled. Now I am differentiating this equation with respect to temperature at a constant pressure. So dou V by dou T at a constant pressure becomes RT by P minus, okay, this minus sign becomes a plus here. Y plus the T is in the uh, T is in the denominator. So it becomes minus 1 by T. So it is minus becomes plus A by RT square. So now what happens? From this equation, I am taking this B out. V minus B is equal to RT by P minus A by RT. Now you take this P this side. P into V minus B is equal to RT minus AP by RT. See, entire term I have multiplied with P. So from this, minus RT is equal to minus P into V minus B minus AP by RT. I'm just changing this sign. RT is equal to P into V minus B plus AP by RT. Now dividing both sides by PT. RT by PT, is it right? Is equal to P into V minus B by PT plus AP by RT into 1 by PT. I'm just readjusting. What I'm getting here is R by P is equal to V minus B by T plus A by RT square. So this RP, actually this is here. So instead of this RP, I'm substituting this entire term. So what I'm getting is dou V by dou T at a constant pressure is equal to V by T minus B by T plus A by RT square. Here is another A by RT square. So what I'm getting? T into dou V by dou T at a constant pressure is equal to V minus B plus 2A by RT. So now the V can also be taken this side. So T dou V by dou T at constant P is equal to minus V is equal to 2A by RT minus B. So from this, I can write this is a normal thermodynamic equation. V is equal to T into dou V by dou T at P plus dou H by dou P at a constant temperature. From this, what I am doing, minus dou H by dou P at constant temperature is equal to T into dou V by dou T minus V. Actually, this equation is a very famous thermodynamic equation. So what happens? Dou T by dou P at a constant H. This is the mu JT, actual definition for mu JT. What I'm doing, look here, this is what we are trying to arrive at. This is the term we have derived from this equation, but the same particular part is already present here. So this is what is substituted here. Instead of this place, I'm going to write this one, 2a by RT minus B, 1 by Cp. So I have completely changed the equation into dou T by dou P at a constant H is equal to 1 by Cp. Instead of this entire term, minus dou V by dou T P minus V, which is taken from here, which is actually dou H by dou P at a constant temperature. Instead of this entire term, I am going to write 2A by RT minus B. So this is the Joule Thomson coefficient of a real gas. What happens now? The Joule Thomson coefficient becomes positive when 2A by RT is greater than B. The Joule Thomson coefficient becomes negative when 2A by RT is less than B. At inversion temperature, exactly at a temperature where the Joule Thomson coefficient becomes 0 is the condition where 2A by RT is equal to B. So I can write what is that temperature, which is called the inversion temperature Ti, which is equal to 2A by RB. So with this, we come to the end of the presentation. You can take the book and you can see the Joule Thomson coefficient and the inversion temperature. So I suppose you might have understood. Actually, I was a little bit fast, but when you come to the class in person, I can explain things to you. If you are not able to understand anything now, don't worry. You just write once and see, then you will easily understand. There are so many absentees. I'm putting the slides once again. You just have a look, or if you want to take a snapshot, or you want to write, you write. Just I put a slide for some 10 seconds. You want write? You write or take a snapshot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 9, 8, 7,